Yes, I hope I'm audible to all now. So, very happy to see the strength, that is the 52. I hope the same strength will remain throughout the session so that you will not leave the session in between. The reason is this is one of the very important mathematical oriented subject where you have a lot of mathematical equations and try to understand those mathematical equations, and then we are supposed to implement the same equations in MATLAB and analyze the various uh, the aspects of mathematical equations with respect to digital signal processing. See, what we are doing is, point should be very clear. We will take the help of mathematics, that is the Fourier transform, Z transform, and Laplace transform. We take the help of these transforms and then we'll try to apply for the signal processing applications. Mainly, we are concentrating on the digital signals, and then we will restrict our the mathematics with respect to discretization of signals. So where you must have a thorough understanding of these mathematical equations, why, what, how it works. Then second point is how we are supposed to take that mathematical equations to analyze a signal processing applications. Then the same signal processing applications we will go for implementing with a practical approach by making use of uh, this MATLAB help. Okay. Now, today in this class we will discuss about the properties of DFT. So let me share my screen here. Okay. Okay. I hope the screen is visible now. So the properties of DFT. So now is it visible, guys? Put it in chat box. I'll just switch between my chat box and the screen. Okay. Fine. Thank you. Uh, okay. Before going to the properties of TFT, so wherein it is purely mathematics, right? So why we require this mathematics? Why we require this the Fourier series and Fourier transforms? Why we go for understanding the properties? Properties ಯಾಕೆ ಬೇಕು? Why properties are required? The main intention in going with this is all about frequency domain analysis. Most of the times we call it as frequency. In order to go for analyzing frequency domain analysis, then we require these properties knowledge. See, there are signals which is always all the time which will be in the time domain. Then time domain signal, the signal we have, what we see will be in a time domain. So we try to go for frequency domain for analysis purpose. Frequency domain. So now when it is frequency domain, okay, so we apply some mathematics for this. See, either from moving from time domain to frequency domain, we have a different mathematical tools. Maybe it is a Fourier series, maybe it is the Fourier transform, or even maybe it is the Z transform, Laplace transform. All these transforms does the same thing. That is, we are moving from time domain to frequency domain approach. Then we look into how the signal behaves in time domain and how it is going to be changed or how it is going to be analyzed in frequency domain. Say for example, if a signal in x of t is a continuous time signal, right? It is a continuous time input signal which is in time domain. So we say that x of s after applying the Laplace transform for this, right? So this is with respect to Laplace transform. So similarly, if now the point should be very clear, so that so we use Laplace transform, we use Z transform, okay, we use Fourier transform. All the three mathematical transforms are used to move a signal or to transfer a signal from time domain to frequency domain. Right? So now the question arises, when to use Laplace, when to use Z transform, and when to use the Fourier transform. Right? So, okay, now in the network analysis, you might have observed the signal wherein the signal is all the time with respect to the continuous time. So you apply the voltage Vi of t, right? So there will be a which is going to be connected with some passive elements like RLC circuits. Then you analyze this, there might be a one switch here like this. So this is how one of the circuit may be. So now you want to analyze, this is with respect to time domain. Then when a signal is time domain, input is time domain and continuous time domain signal. In such cases, see, continuous means I should have a integration. If you observe the Laplace transform definition, so this is somewhere else something like f of x into e to the power of minus st into dt or dx, right? So this is how the Laplace transform definition stands. F of s is equal to, right? So which means that whenever my signal is continuous time and a signal is the continuous time signal, then if I want to analyze its frequency domain, then I will be moving for Laplace transform, right? Now this is one point. Okay, and the another most important is, apart from this, the complex exponential signal. The input is also the complex exponential, because look at this, this is not only the Vi of t, this is having some angle, right? So this will be angle. What does the angle represents? Which is nothing but a phase shift, which is nothing but a frequency shift. So when you have such exponential input signal, then again we go for applying the Laplace transform in such cases. Now the signal is discrete. Now the signal is discrete time. Then we have a different transforms. Maybe it is Fourier transform or Z transform, right? So now the point is very clear here. While moving to Fourier transform and Fourier series, that's already we have discussed it in one of the class, where if the signal is periodic and if the signal is non-periodic, based on that we apply Fourier transform or Fourier series, right? If the signal is periodic signal and continuous signal, I repeat once again, if the signal is periodic signal and if the signal is continuous signal, then I apply Fourier series. If the signal is aperiodic, the way I took an example of your heartbeat or heart pulse, like the speech signal, all these are aperiodic signals. And if I want to apply or if I want to move a frequency domain, no, time domain analysis to frequency domain analysis, in such cases I apply the Fourier transform. Now the point is, this is all the time when with respect to signal I'm speaking. With respect to signal, see, any signal must be passed. I'll take one more. Any signal that you take, the signal analysis are done with these Laplace and the Fourier transform, right? Then what about the analysis of system? Now see, any signal has to be passed, it has to pass with some system. Then I need to know if and only if the signal is stable, the system is stable and system is non-causal and system is memory or memoryless, then only if the system is stable or unstable, only then I can able to pass the signal. If not, again it is not possible. Okay, now again I should analyze whether the stability of the systems in such cases I try to apply, because most of the time these system that what we build is a electronic systems, and all the electronic systems are with respect to the digital inputs, right? Or it's almost like your the logic design circuits what we use. So then such system are to be I need to check the stability of such systems, and whenever we have to analyze the stability of the system, then again we go for applying the Z transforms here. So to analyze the stability of a given system or even whether a signal is going to be stable or not. To give one the beautiful example for this understanding is, see, we build the civil engineers build a hanging bridge, right? The hanging bridge, the bridge is a system now. What is the input for the bridge? Maybe a wind or maybe a floods. So maybe a wind at different speed wind maybe we don't know. So at one time there is a chance of collapsing that particular bridge, but we try to build a bridge in such a way that to withstand the maximum wind speed, right? So now the system has to be stable condition. Now you can observe that the signal wind can be analyzed using a sinusoidal waveform or not. So then the input signal for my system bridge is this kind of signals. I apply and I see to that at what various speeds and various frequency, because all the time any wind signal or any the flow of river signal can be mathematically can be analyzed using a sinusoidal waveforms. So this I have an input in the form of sinusoidal waveforms. I now apply a continuous, since the signal will be a continuous time, and obviously it is a periodic signal, because you cannot say that the speed of a wind remain constant throughout a day or throughout a year. So obviously it is a periodic signal, and again there will be a continuous kind of signals here which try to pass through that particular hanging bridge, and I need to know that whether the bridge is going to be stable or not. Now to analyze this, I will be applying the Laplace transform to analyze that particular bridge, hanging bridge. Now I will be applying whether this these kinds of signals are able to handled by this system or not, or even how long it will going to able to handle these kinds of signals, and that time I will be applying the Z transform. This is one simple examples that I'm trying to give here, just to make you aware of the importance of mathematics in the real time applications, right? Okay, now now the question arises, why why frequency domain? Why we always go for see why I'm trying to discuss these topics is these kind of questions is, see, I always say when I say that properties, I will be saying that, see, if x of n is a time domain signal, its frequency domain is x of k. I just tell this, but the you should understand why we will be moving from time domain to frequency domain. What is the purpose of analyzing any signal going into frequency domain? Why it is required? The reason is, see, I take a very good example so that you can understand this very clearly. So you have a beam of light which we call it as a white light, right? white light. Now if I keep up, you all you have might have studied this experiment in your PUC or even in engineering physics, where when I keep a spectrum, what is possible? What is the possible outcome here? I will going to get seven different colors, right? From white light will going to split into seven different colors. So that's what we call it as with chaos, right? So violet color, blue color, green color, yellow color, and orange color, and one more is red color. So this is what when I keep a prism, so this is what I'll going to get the different seven different colors. So what does it mean? What does it mean? So which means that white light is not a actual white light. It is the combination of different colors which gives me a one color that looks like a white light. The other way I'm telling, other way if I want to speak in a mathematical language, there is a one frequency F, which is nothing but a white light, which is not a single frequency signal. It is a multiple combination of F1 frequency, F2 frequency. See, when I say that different light, obviously I assume or I take this as a signal. So maybe the white light is having or traveling with a frequency of F1, the blue color light will be traveling with a frequency of F2, then one more signal F3, then one more signal F4, one more signal F frequency of F5, one more signal of frequency F6, right? So there are the six different combination of different frequencies. The combination of different frequency is possible to get me this white light, is it not? See, which means similarly, if I take any signal, I'll come back. So this white light is nothing but the this is what we call it as the first time the Newton coined this word called spectrum analysis, or frequency analysis, or frequency analysis. When why we perform this, I'm going to get to know that which all the different frequency components are present in my white light. So this is actually a time domain, and this is what we call it as a spectrum analysis or frequency domain, right? Now this prism is a simple example where you get to know that the different combinations of light. Now I apply a signal. So any signal, let me take the ECG signal. So do you mean to say that ECG signal will be having only one component of frequency F1? Definitely not, because you can observe the signal. So there is a different values that are going to be present in my signal here. There are different frequencies here. Every instant of time, the frequency is getting varied. So hence, this signal will look like a single signal, but which comprises of F1, maybe F2, maybe F3, maybe so many different frequency components. So this is a single signal. Say for example, if I want to analyze my voice signal will be having the different components of signal frequencies that is present. Now I want to analyze my speech signals. Now I want to analyze my ECG signal. All these signal looks like a single signal, like a white light. Now I need to split this into different components: F1 frequency, F2 frequency, F3 frequency. Now what you do? I cannot keep a prism there. So I must use some mathematical equations. That is what you already learned. If the signal is continuous and you learn about a periodic signal, so that you will apply. If this you look into the input signal now, if signal is continuous and periodic, you remove this prism, then you have a mathematical this thing that is Fourier series, right? So now it will split into individual frequencies, then again you will analyze this. Or else, if a signal is aperiodic and if a signal is continuous, then you have a Fourier transform. Which will going to split that particular frequency into different components of frequencies. Then again, it is very easy for me to analyze, right? So again, if I want to get back my white light, what you will be doing? So you will keep a prism in inverted mode, right? So this is how we keep the we try to keep back uh, we try to keep this. Then again, we pass all the frequencies, that is all the different lights. Then again I could able to get the original white light, right? So once again, all the time what we see in the real time is white light. Only for analysis purpose, I keep a prism, I go for a spectral analysis. Similarly, all the signals are time domain signals, but whenever I want to perform, I want to analyze, I go for keeping a prism kind of thing, which is nothing but here it may be Laplace transform, or it may be Fourier transform, or it may be Z transform, or it may be Fourier series. All these mathematical equations will give me the frequency analysis operation. And once we have a frequency analysis, then later on I can able to analyze the individual frequency components, as I told you in case of white light. Again, I want to come back to the original light, white light. So what we do? We just go for inverted prism. In mathematics, we go for inverse Laplace transform, in inverse Fourier transform, or inverse discrete Fourier transform, or inverse Z transform, and it continues. I hope you got a clear idea of the importance of the frequency domain analysis. Let me come back to the Google Meet. Let me take up any questions are there. Any questions, guys, here? Any questions? Did you understood the importance of frequency domain? Was it convincing? Why we go for the frequency analysis? Okay, fine. Now this is where, okay, thank you. Now this is where we should go for. Now I will go for properties. So where a time domain signal will be something, and maybe in the time domain, in the signals and systems, you have learnt different operations. That is the time shift operation. Then how it will be look in your frequency domain operation. You have understood a convolution, basic simple convolution, which is going to be performed in time domain. How it when I move to the frequency domain, how actually the frequency domain operation is going to be performed. So all these kinds of properties, that's what we will going to understand in upcoming slides. Okay. Okay. So these are the properties of DFT that we will going to discuss. So one is a periodicity property, linearity property, circular time shift, time reversal, circular frequency shift, and circular convolution. And followed by two more. One is symmetry. This is very important. One of the most important property, that is symmetry property. Then one more is the circular time shift and circular frequency shift and circular convolution. You will get to once you understand this circular time shift, it is very easy for me to go for circular convolution operation. So and periodicity and linearity are very simple and straightforward. You might have learned the same thing in the Laplace and the Z transform, and even in signals and systems. That is probably in one of the chapter. Probably even Fourier series itself, chapter is there. So there itself you might have learnt about this. I quickly go with the understanding of the periodicity, linearity, and circular time shift. Today we'll try to cover these three properties, and then one simple example on circular time shift. To obtain using this property, we try to obtain the set. What is that? DFT. Okay. Uh, then what is periodicity property? So, what do you mean by periodicity in uh, the time domain? In time domain, if the signal is x of n, it is periodic. So, as I told you when we discuss the when the moment you move for what is that the frequency analysis of a periodic signal by applying a discrete Fourier transform, the this signal will be periodic in nature, is it not? So if suppose if the signal input itself is a periodic signal, that is x of n in case of here uh, okay x of n, then its DFT will be x of k. This is well known fact. Then if I shift by n point sequence, after, which means that if the same signal is going to repeat after some certain period. See, since it is a discrete, I am trying to increment this value by a discrete value itself, one constant value n. Say for example 4-point DFT or 8-point DFT as such. That means if a signal x of n is equal to 0, 1, 2, 3, assume that after this uh, x of uh, 3 again the sequence repeats. That's what the meaning here. In such cases, so if the signal is this periodic, then this will be a periodic signal, and its DFT is also if I take a DFT of this, so this will be x of k plus n. So that is what the meaning here. Okay. Uh, Here you don't have a proof for this. No need to go for proof, but if you want to have, you just uh, go through the textbook like Uday Kumar textbook. But right now we for this course for your batch we removed all these proof. So better you go for Uday Kumar, and if you have any doubts, please let me know. I'll just uh, make sure that your doubts are going to be clarified. So any doubts, guys, don't worry. At any point you have any queries, feel free to ask. No issues. And the linearity. The meaning of linearity is combination of two or more signal. That's it. Okay, so there is a x1 signal. Okay, there is a x1 signal, and if you obtain its DFT, so obviously this will be x1 of k, right? So again, there is a one more signal x2 of n. Okay, then its DFT will be x2 of k. Okay, now linearity is nothing but I am trying to add those two signals, right? Add performing by applying some constants, a1 as a constant and a2 as a constant. I multiply with some constant the input signal, and another second input signal is also going to be multiplied, and we are trying to add those signals. In such cases, what happens to DFT? So it is very simple and straightforward. So this signal is also added with scaling the input signal, so input constant. So this x1 of k is also scaled by a1 times. This x2 of k is also scaled by a2 times. Then since we are adding those two scaled versions of a signal, so obviously, so this will be y of n. Y of n is nothing but a1 x1 of n plus a2 x2 of n. So y of k will be, so y of k will be, so this signal will be a1 x1 of k plus a2 x2 of k. So this is a very simple linearity property. You also come across these types of property in mathematics as well as in Laplace transforms, right? Now, coming to the third very important topic, circular time shift property. Leave about this circular. Let us understand the time shift property. What do you mean by time shift property? So time shift in your signals and systems cases where you have a x of n as an input signal, right? You will be trying to shift this signal by L times. Say for example, you have a signal called x of n is equal to, let me assume that 1, 2, and okay, 0, let me take a 0, 2, 3, right? So which is nothing but the pictorial representation of this will might be looking like this, x of 0, which means that this is time value. The y-axis stands for time signal, and the second signal x of n equal to 1. When n equal to 1, the amplitude is 2. Then when n equal to 2, the amplitude of this signal is 3. That is what x of n is all about, right? So this is how the pictorial representation of this is going to look like. Now, if I want to shift this by one time unit, so which means I'm just trying to shift the x of n. See here, I'm performing on a, see, this inner value always talk about time axis, is it not? So you make sure that this is n minus 1 now, which means that I am trying to make an operation on time shift. The value of time is getting shifted now, which means that if I observe this, let me take this as a new signal. Let me assume that this is a y of n. So this is y of n is equal to x of n minus 1. We have x of n. X of n is defined like this, right? Now what will be the new signal? Which means y of 0. Y of 0, how do you calculate? X of n value becomes 0, and this is minus 1, which means that x of minus 1 signal will come and sit in y of 0 position. What is x of minus 1 here? We don't know, it is 0, right? So if I perform this, so this 0th position will going to come and shift here, right? So this will be 0. Okay, now y of 1 value. So what will be the y of 1 value? So let me write here. So y of 1 value. So x of n is 1. I am trying to shift it by one more 1. So this means the new value first position should be x of 0 value. So this is going to be shifted. So again this value is again 0. Similarly, if I go for, then x of 2 value will going to get me the amplitude of 2, x of 3 value will going to get me the amplitude value of 3. This is how the value is getting shifted by 1, right? So this is all about time shift. Time shift. Now I'm coming to concept by including circular time shift. What do you mean by circular time shift? This is very important. Where x of n x of n is a sequence of n point DFT of n point DFT, then its circular shift will be x of n minus L times of mod n. So which means that all the time the signal in a time domain, the signal will repeat back with the same value, since all the time we will be discussing these signals are periodic signals in the frequency domain. When I say that circular time shift, the time shift is going to be performed in a circular way. Okay, now just let me take up a same example. What was the example here? Okay, let me take a different example here so that you can understand much better. Okay, x of n. Let me consider x of n is equal to 1, 2, 3, 2. So this is a normal signal. Now I want to perform circular time shift. Let me assume that L equal to 2. So how many point DFT it is? How many point sequence it is? This is 4 point sequence. A 4 point sequence input. Now I want to perform circular time shift. Circular time shift. So later in point of time when you go for frequency analysis, definitely this signal will be a periodic, and since it is a discrete, so obviously it it must repeat its value, right? So this is how the new value looks. Now let me explain you how I should perform the circular time shift. So now circular time shift y of 0, y of n equal to, let me take a new page here. So I'll just so y of n is equal to x of n minus the value of L is 2 in this case, and this is 4 point sequence, and this is circular time shift. So x of n was 1, 2, 3, 2. X of n was 1, 2, 3, 2. Now just find out y n equal to 0, new signal y of I'll by put n first n equal to 0, then x of 0 minus 2, and this is mod value as I told you, which means that there will be never a negative value. So this is not minus x of minus 2 with mod value of 4. What does it mean? Which means that x of, you need to take a positive value all the time. So this, since this is how we need to perform during the negative values, that is 4 minus 2, which means that the new signal y of 0 must be x of 2 position, that is 0, 1, 2, 3, which means that y of 0 will be 3. That is what the meaning. Similarly, y of 1. What is y of 1? So x of n value is 1. 1 minus 2. Again you will going to get a negative. So the signal cannot be a negative. That you understand? The signal must not be a negative. So which means it is not minus 1 here. It is 4 minus 1, which means that x of 3 value. What is x of 3 value here? 2. Right? So y of 1 new value will be 2. So similarly put n equal to 2. So this will be x of 2 minus 2. So there is no point of negative because I just directly got a 0. So this is x of 0 itself, that is 1. So see, the last x of y of 3 value is x of 3 minus 2, that is nothing but x of 1. What is x of 1 value here? So that is 1. Sorry, uh, this is 1. No? X of 1 is 2. Now what is the new signal? Y of n. Y of n is nothing but x of n minus 2. What happened? Okay. No, that's what the example I took here. Uh, so, sorry. X1 of n, we took this as 1, 2, 3, 2, and we asked you to obtain the circular shift of x1 of n minus 2, right? So what? How do you perform? That is, let we consider x y of 1 y of n is equal to x of n minus 2, and this is a 4-point DFT, right? So this is 4-point DFT here. So just go on applying y equal to c n equal to 0, so that we're going to get 0 minus 2, and this is 4 points. So we call this as a mod operation. So this must be x of 4 minus 2, that is equal to x of 2. And what is the value of x of 2 in this case? So this is 0. So this is 0 indexing 1, 2, and 3. So this will be 3. Similarly, y of 1 is equal to x of 0 minus 1. This will be x of 3 value, which means that x of 3 value is 2 in this case, right? So similarly, y of 2 is equal to x of 2 minus 2. So this will be x of 0. X of 0 is nothing but 1. And finally, last value, if I calculate y of 3, so I'll going to get 2, right? So I'll going to get 3 minus 1, that is 1. The 3 minus 1, 3 minus 2, that is 1. So y x of 1 a value I'll going to get. So new value y of n, or circular shift of my input x of n minus 2 will be, so what is this? The first sequence is 3, the next followed by 2, then 1, then 2. So this is how the circular time shift operation is going to be performed. So let me give you one more example. Just quickly try this and give me the answer. Okay. Consider x of n is equal to, consider x of n is equal to, x of n is equal to, let me give you 0, 4, 3, 6. Okay, perform a circular convolution of x of n minus 3. Can you do it quickly and let me know the answer? I will be waiting in chat room. You can observe here in the previous case, just obtain the value of first sequence. So this is how I call this as a circular shift. So when you perform, the previous example was 0 minus 2, which means that 4 minus 2, second position. From this position, you just move in a uh, the anti-clockwise direction. So this is how we try to take it as 3 comma 2 again 1 2, right? So that's what we get the answer 3 2 1 2, right? So similarly here also I take a same technique here. So this is first sequence is 4 minus 0 minus 3, that is x of minus 3. X of minus 3 is nothing but 4 minus 3 1, x of 1. So x of 1 is nothing but 0 1. So this is my first sequence. From here I start. From here I start, I move forward direction, then I can, since it is circular, the last value is this, which means that the answer must be 4360. Am I right? So this is a very simple technique. So and a shortcut method. So most of you have tried with this and you got the correct answer. So that is one where we go for shortcut method. I hope you got to know about how to calculate the shortcut method. So once again, you just perform this. X of n equal to 1 3 5 7 1 3 5 7. So just perform x of n minus 2 quickly. Quick. It is 1357. So how do you perform? Yes, very good. 5 3. What is the first sequence here? What is the first sequence here? So that must be second value, that is 4 minus 2 2. So that is 0 1 2. This is the first value. So since here, from here I move around and I'll come up with this, that is 5 7 1 3 1. So this is my the circular time shift operation, right? So now I'll quickly move to the property here. I quickly move to the property here. So x, if x of n is my input signal, its DFT will be x of k, right? So that is what circular time shift property. Time shift property. Okay, what do you mean by circular time shift? So this is the time shift operation that is going to be performed. Is it not? So what will be its DFT? Its DFT will be x of k, which means x of n in the n x of k ತಗೊಂಡಿರ್ತೀರಲ್ಲ, the same x of k will be there. It is just going to be multiplied with e to the power of minus j 2 pi by n kl, k times the shifted value, that is l. So this is what the time shift property talk about. Is that clear, guys? So this is time shift, and we'll try to solve one example on this, and we'll wind up the class. Now, okay. Now consider, so which means, see, only thing is take the x of n DFT this, and you do a time shift operation here. You will going to get some one more sequence, so that I will be calling it as y of n or x2 of n, right? So again, don't take the DFT, just you already have a DFT. For that DFT value, just multiply this with each value. Let me take an example so that you will going to get a clear idea here. That is example, consider x1 of n is equal to 1 2 3 2. X1 of n is equal to 1 2 3 2. Obtain x of x1 of n minus 2, a circular shift. Obtain DFT of obtain DFT of x1 of n minus 2, circular time shift using suitable property. So this is how a question will be given using suitable property. So what is that property? So it is nothing but I am doing a circular time shift in the time domain. You need to obtain DFT of this x1 of n minus 2 by using property itself. The one thing is there are two ways. One is x1 of n you already have, and what is x2 of n here? Let me take y of n, y of n, y of n. What is y of n here? x1 of n minus 2, a 4-point sequence. Here, what is this signal y2 of n? x1 of n, that is y2 of n will be equal to, what will be y2 of n will be equal to, that is nothing but 3 to 1 2, right? So this is 3 to 1, 3 to 1 2. So this, so you know that you can easily find out y of n DFT, right? Y of k can be solved very easily. This DFT already you know how to perform using the matrix method. But what we are asking to go with a suitable property. What you are supposed to do? You should take DFT of this x1 of k. Okay, x1 of k. Then multiply this x1 of k individual value with e to the power of minus j 2 pi n kl. Okay, try to solve this example. If you get the answer, well and good. If not, tomorrow I will discuss the answer. Okay. So what you need to do? Obtain x1 of k DFT. Apply the matrix method. Try to find out the x1 of k. Then each value of k you will be getting x of x1 of 0, x2 of 0, x1 of 1, you will be getting x1 of 2, all the DFT values you will be getting. Individual values you need to multiply with e to the power of 2 pi n. What is n here? 4. What is k for the first value? It is 0. What is the value of l? It is shifted value is l, 2. So this is how you are supposed to multiply. 2 and 2 get cancelled. 2 ones are 2 twos are. So this is nothing but e to the power of j into 0, and this is nothing but x1 of 0 into 1. So that's how you are supposed to do. Try to solve this example and see to that y2 of n, y of n you already get 3 1 3 2 1 2. Once again you obtain the DFT of this DFT, and through the property you must get the same answers. Any doubts? Any doubts? Try this, guys. Don't worry, even if you don't get tomorrow, with a lot of pay, with a clear intention and with very clear explanation. Once again, I'll solve this example. I hope today's in this lecture you don't have any doubts as such. If you have any doubts, please let me know. Don't worry, at any point of time, if you have any sort of doubts, feel free to